In this lesson, we're going to talk about real numbers. We are going to save absolute value for a later date. So, if you think of the real number system, there are a bunch of numbers that comprise the number line. And this is what we should think of when we think of real numbers, the real number line. So if we look at all the numbers on the number line, we can start building sets that create the set of real numbers. So we're going to first begin with natural numbers. Natural numbers, well, if you think back to when you were a child and you started counting things, how did you count? Well, you had 1, 2, 3, 4, etc. These are your natural numbers. Your natural numbers, also known as counting numbers, are the set of the numbers we use for counting. And here are some examples. Now, the symbol that we use to represent natural numbers is an N with the special bar in it. Now, if we add the number 0 to the set of natural numbers, counting numbers, we get whole numbers. So now we have the set of natural numbers in 0, and they give us whole numbers. The symbol to represent whole numbers is this special W. And note some examples. Now, if we now look at 0, the set of natural numbers, and their opposites, so in other words, negative numbers, if we include negative numbers, we get the set of integers. So integers are natural numbers and 0, and the opposites of the natural numbers. And the symbol for integers is a Z with a special bar. So we're growing our sets of numbers to create the number line. Now, if we look at all the numbers that can be written as a ratio, a fraction of integers. So, for example, if we look at numbers A that are integers, B that are integers, and we must say that B, the denominator, cannot equal 0, or it makes an undefined expression. If we look at all those numbers, so in other words, all the numbers in between our integers that can be represented as a fraction, we get the set of rational numbers. And if we convert these fractions to decimals, we're going to get decimals that terminate, that stop, or that repeat. And so examples would be negative 2/3, and if we were to convert that to a decimal, it would be negative 0.67 with a bar over it to denote that the 6/7 is repeating. We can also look at the fraction, the ratio 2/5, which if we converted to a decimal is a finite decimal, 0.4. It terminates. And we can even look at whole numbers, which can be represented as fractions with a denominator of 1. So these are your set of rational numbers, represented by the symbol Q with a bar. Now, if you look at the set of numbers that can't be written as a ratio of integers, can't be represented as a fraction, you're going to get the set of irrational numbers. Now, irrational numbers, well, if we look at them in decimal form, they do not terminate or repeat. So if you think of an example, perhaps you think of pi. Pi is irrational. So is a fraction involving pi where pi is in the numerator. Or perhaps the square root of 2. And if we look at its decimal equivalent, well, it's approximately 1.41421, and it goes on forever and ever and ever, but it doesn't repeat, and therefore it doesn't terminate if it goes on forever and ever. Now, there's no widely used symbol for irrational numbers, However, we're going ahead and use the cursive IRR. So if we look at these rational numbers that contain integers and whole numbers and natural numbers, and we combine those with the set of irrational numbers, we're going to get the real number line, the set of all real numbers. So the set of all real numbers are either rational or irrational numbers. They're all the numbers on the number line. So the entire number line, the real number line. And the set of real numbers is represented by the letter R with that special bar. So now, what if we're given a set of numbers and we want to order them from least to greatest? So we're looking at the number line and we're seeing which one falls furthest to the left on the number line to find the least value. Well, first let's look at some of these values and figure out what their decimal equivalents are. Well, we know that pi is approximately 3.14, but it goes on forever and ever and ever and doesn't repeat with a pattern. Square root of 5 is approximately 2.236. It goes on forever and ever without a pattern, doesn't repeat. Now, if I were to arrange these, the smallest value, well, negative 11 halves, we know equals negative 5.5. That is the smallest value. The next smallest value is square root of 5, 2.236. The next value is 2.3, 2.6752 is next to the right on the number line, then the whole number 3, and then pi. So if we were to classify these, we'd see that negative 5.5, which was a result of dividing negative 11 by 2, is a real number and also a rational number. Square root of 5 is a real number but irrational number. 2.3 is a real number and a rational number. 2.7652 is a real number and a rational number. 3 is a real number, a rational number, an integer, a whole number, and a natural number. So 3 belongs to all of those. Pi is a real number and an irrational number. Now, there's many different ways of representing intervals. So in other words, parts of the number line. So if you are given it in words, can you convert it? Can you represent what's being described, the set of numbers, on a number line visually, in interval notation, and as an inequality? Well, first, what is interval notation? Well, interval notation means we're dealing with an interval. If we don't include the endpoints on the interval, it's an open interval, or if we do include the endpoints, it's a closed interval. And we always represent the numbers in the interval with the smallest number first. I should point out that you can have one side that is open and the other side that is closed. They don't both have to be the same. As an inequality, we use inequality symbols. Greater than, less than, greater than or equal to, meaning we're going to include an endpoint, less than or equal to, meaning we're going to include an endpoint. So again, to stress, if we are including the endpoints, we would use for interval notation the closed intervals. We would use greater than or equal to or less than or equal to with inequalities. If the endpoints are not included, we would use open intervals, and we would use either the greater than or the less than symbol. So let's first look at all numbers that are less than 3 on the number line. So here's our number line. Let's find 0. Let's find 3. And if I'm looking at all the numbers that are less than 3, it would look like this visually. So that's how we would graph it on the real number line. As an interval, well, what's the smallest value? Negative infinity. It goes all the way to the left infinitely in the negative direction. The largest value in the interval is 3, and it's an open interval because we do not include 3. It doesn't say numbers less than or equal to 3. As an inequality, we'd say, okay, I'm looking at all numbers, let's say x, that are less than 3. Let's try another example. We are looking at all numbers greater than or equal to negative 2. So let's find negative 2 on the number line. 0. Here's negative 2. We're looking at all numbers that are greater than or equal to negative 2. So we're going to enclose that endpoint because it could include negative 2. So we include negative 2, that's the smallest value, so that's the first number in the interval. And then it goes on forever and ever in the positive direction infinitely. And we always use an open interval for infinity. Now how would we represent this as an inequality? Well, we're looking at all values x, all numbers x, that are greater than or equal to negative 2. So here we have it in interval and inequality, using inequalities. Now the next example are saying, okay, all numbers between 2 and 4. So let's find where those are on the number line. I like 0 as a placeholder. 2, 4. Now I'm looking at all numbers between 2 and 4, not including those endpoints 2 and 4, but between. So we would use open interval, the smallest value is 2, largest value is 4, again open interval. So how would I represent this using an inequality? Well, this would be a compound inequality, an extended inequality. 2 is the smallest value, 4 is the largest value. We're not including those, but x is any number in between, greater than 2 and less than 4. Now the next notation that we're going to use to be able to represent sets is called set builder notation. And it's always represented with these curly braces. The first thing that you include is the variable or variables that you're trying to describe. So in this case, we would read this as the set of all x's, and then this bar here can be read as such that, and then everything that follows the bar are all the statements about x. So what specific conditions does x need to meet? So let's take a look at a few examples and see how we would represent them as set notation. Actually, not as set notation, but in two other notations. We're going to look at roster notation, where we just list the numbers, and we're going to look at interval notation, which we've talked about. Now, I like to draw pictures where I can to help me understand what I'm looking at. Visualize the numbers first. If I'm looking at all real numbers, so I'm looking at the number line, I'm looking at all real numbers except 1. So I'm not going to include 1, so I have an open circle on 1, but I'm looking at all other real numbers except that. So can we list all those numbers? No. So therefore we have no roster notation. We cannot list all of those numbers. It's infinite. Now, can we represent it in interval notation? Sure. The smallest value is negative infinity, and remember we use an open interval for infinity. Then we go to 1, but we don't include 1. Or it could be any of the numbers on the other side of 1, to the right of 1 on the number line. So or, we use the symbol for or, 1 to positive infinity. Now let's take a look at all the numbers within 3 units of 2. So I'm going to find 2 on the number line, and I'm going to go 3 to the right, so that would take me to 5, and 3 to the left, which would take me to -1. Now, can I list all of those numbers? That's 3 units away from 2. All of these are within 3 units away from 2. All of these are within 3 units away from 2. So I can't represent those using roster notation as a list, but I can represent it in interval notation. The smallest value is -1, and it's included, so it's a closed bracket, closed interval. And 5 is the largest value, so I'm going to put 5 as the second number. And again, it includes it, so I'm going to close the right-hand side of the interval. Now let's go ahead and take a look at all positive odd numbers. Well, if I were to visualize that on the number line, I'd say, okay, positive odd numbers, that's 1, 3, 5, and I could keep going forever and ever and ever. Now, can I list those? Sure. 1, 3, 5, 7, and then I'd put a comma and 3 dots to show that this goes on forever. This is an infinite list, an infinite set. Now, can I represent it as an interval? No. These are discrete little points on the number line. This is not an interval, so there is no interval notation. We can't write it as an interval. So now let's look at another example. Let's look at all the numbers less than or equal to 4 and use that information to visualize first all numbers less than or equal to 4. So less than or equal to we fill in 4 and then shade to the left for less than. Interval notation, well, the smallest value is negative infinity. 4 is the largest value in that interval, and it includes it, so I'm going to close the interval on the right. As an inequality, I'm looking at all x values that are less than or equal to 4. And set builder notation, okay, set of all values, and I'm going to call them x, such that x is less than or equal to 4. Now on this slide, we have the properties of real numbers. This chart can be found in your book. So I want you to go to this section in the book, and I want you to complete or come up with examples or look at their examples and populate this column, this last column. So, commutative property of addition, and you need to know these names and be able to recognize this. So when you're changing the order, when adding, it doesn't affect the sum. So I want you to come up with an example. See, the order doesn't matter. Order doesn't matter. A plus B equals B plus A. Now the commutative property of multiplication says again, now when we're multiplying, order doesn't matter. A times B equals B times A. The associative property deals with grouping. So whether you're grouping a sum or grouping a product, changing the grouping when adding doesn't affect the sum. So as who you associate with is what I normally think of for the associate property. We have a group here it's equal to the sum of with this grouping. And same thing here in multiplication. The distributive property, you should recognize, well, if you have a term multiplied by a parentheses, you have to distribute what's on the outside of the parentheses to each of the terms inside the parentheses. The additive identity property says that 0 can be deleted from a sum. So if you add 0 to anything, you get back what you started from. Or if you add something to 0, you get what you're adding to 0. The multiplicative identity property says that you can multiply anything by 1 and it doesn't change the value. So anything times 1, well, we should say non-zeros, or we get the same answer, equals 1 times that value. The additive inverse property says the sum of a real number, say A, and its additive inverse. So here's the key, the additive inverse, the opposite, gives you 0. A number and its opposite, when added together, gives you 0. The multiplicative inverse says that the product of a real number A and its multiplicative inverse, 1 over that value, equals 1. 1 over a real number times the real number, that number in the denominator, again, we're not looking at 0 in the denominator, equals 1. The closure property states that when you combine any two elements of the set, the result is also included in the set. So adding two real numbers, you're going to get a number that is in the set of reals. So look in your book, whether the hard copy version or your electronic version versus my math lab, and try to come up with examples. See the ones in the book or use the meanings to come up with your own examples. Now let's take a look at a few examples. Here you're being asked to find not only the additive inverse, but the multiplicative inverse of each of these. So let's look at the first one, 9. If I'm trying to find the additive inverse, I'm asking myself, what am I adding to this number to get 0? Well, its opposite is negative 9. Now look at the next example. Negative 3/4. What am I adding to that to sum to 0? Its opposite, 3/4. Now let's look at the multiplicative inverse. What am I multiplying by each of these numbers so that the product is 1? Well, the multiplicative inverse of 9 is 1/9. Just invert. What is the multiplicative inverse of negative 3/4? Invert that fraction, negative 4/3. So you're just taking the reciprocal when you're inverting it. Now let's look at a few examples and see if we can identify which property is being used in each example. So in the first example, you see that 3 times 2 equals 6. Well, 3 is a real number, 2 is a real number, 6 is a real number. So if we take the product of two real numbers, we get a real number. Hopefully you recognize this as the closure property of multiplication. Now let's look at the next example. You have a real number 12. You're multiplying it by hopefully what you recognize as its reciprocal, and that gives you 1. So this is the multiplicative inverse property that's being demonstrated. In the last example, you have a real number, 6. You're adding 0 to it, and you're getting the original number. This is the additive identity. Now, what's the difference between opposite and reciprocal of a number? Well, the opposite is the additive inverse. The additive inverse. So 3 and -3 are opposites. The reciprocal is the multiplicative inverse. So we have 3 and its reciprocal is 1/3. Adding these opposites gives us 0. Multiplying these inverses give us 1. Now look at the next 3 examples and let's see if we can figure out if they're sometimes true, if it's always true, or if it's never true. So we can think of examples of where this would work and where this wouldn't work. Maybe come up with a counter example of when properties work. But let's look at these specific examples. We know that the value of B is 3. So A times 3 equals A. Is this always true? Well, I can think of examples where it's not true. What if A is 0? 0 times 3? Well, that does give me 0, so that's true. Is there a time you can think of when this is not true? Well, what if A were 1? 1 times 3 is 3. Well, that's not true. So this is sometimes true, representing the closure property. Looking at the next example, well, if we're looking at the left-hand side, hopefully you'd want to distribute that and recognize that you do in fact get 3A plus 3. So this is always true. And this is the distributive property. Now, if we look at the last example, well, if you take a number and add its opposite, you're going to get 0. If we do the same thing on the right-hand side, take a number and add its opposite, we're going to get 0. So this is always true and represents the additive inverse property. Now on this last page, we're going to look at the intersection and the union of two sets. So the intersection of two sets, let's say set A and set B, is the set that contains all of the elements in A that also belong to B and no other elements. So this shaded region would represent the intersection. So here you've been given two sets and you're being asked to find the intersection. So A intersection with B, which is read A and B, they belong to both A and B. They must satisfy both sets. So what numbers in example A satisfy both sets? Well, I think only 3 are in both sets. So the intersection of these two sets would just be the number 3. In the example B, we're looking for numbers that are in both sets. 1's in both sets, 2's in both sets, 3's in both sets. So the intersection of those two sets would in fact be the numbers 1, 2, 3. Now let's find the intersection of the two sets in example 3. Well, 1's not in the other set, 2's not in the second set, 3's not in the... Well, they don't share any elements. They don't have any elements in common. So if we have no elements in the set, we would read that as null set and use this symbol, or you can use the empty set. So either of these would work. The null set represented by this symbol, or the empty set represented by this symbol. Now, what about the intersection of these two sets? Well, the empty set, the null set, is always a subset of all sets. Now, the next relationship that we're going to look at is the union of two sets. The union of two sets, well, if we have set A and we have set B, or they could overlap, it's the set of all distinct elements in each. So if they did overlap, we wouldn't list these values that they both share more than once. We would read this as A union B, or A or B. So we would write these sets, the union, as all the elements that is in either A or B. So let's look at the first example. Well, the union would be 1, 2, 3, and 4. Now, when we're writing sets, we should write them in increasing order and not list elements more than once. Let's look at the union of the next two sets. Well, they would just be 1, 2, and 3. Again, we list the elements in increasing order and don't repeat numbers. Now, what about the union of the next two sets? Well, 1, 2, 3, 4, 5, 6. And what about the last example? Well, the union would be 1, 2, 3. Now, there are two symbols that you should be familiar with because they will be used in math throughout your mathematical career. This first symbol looks like a little E, and it means is an element or member of. So, for example, we can say 1 is an element in the set 1, 2. Or 3 is an element, in the interval, I should say interval, 1, 7. This symbol with an E with a line through it means is not an element of. So for example, 3 is not an element in the set 1, 2. And maybe we should change these to sets. Let's make them all sets since we're talking about sets. 7 is not an element of the set 0, 10. So we should be familiar with those two symbols as well. If you have any other questions, you should look in your book in chapter P1, where we discuss and